All right, we're going to do an explicit analysis with impact. To do so, we create two parts. The first one we're going to call the main part. That's a 3D solid extrusion. And we are going to draw a sample geometry. As you will see, it's a simple geometry of a 3D solid. And we're going to give it some dimensions. This is going to be actually smaller than that, 25. This value is going to be 5. This one is going to be equal to 6. And this one isn't drawn very well, so we're going to delete this guy and this one. And then give that a dimension of, let's see, 35. And then end the connection here by going straight down, over across. And now we're going to create fillet of 2 millimeters in the interior, picking these two edges. And then pick another fillet with the radius of 3 millimeters for the outer dimension. And that should take care of the part with the depth of extrusion of about 10. We'll say OK. We'll go ahead and assign the material to this. This is going to be aluminum. We'll give it specific properties. We're dealing with the unit of millimeters in this case, so the mass density that we're going to provide is going to be 2.6 e to the minus 6. And then mechanical elasticity, elastic, Young's modulus of 79, GPa, so we want MPa, multiply that by 1000, Poisson's ratio of 0.33. And we give it plastic information. These are some sample plastic information I've generated. 150 0 for the first point, 250 and 0.05 for the next one, and 350 and 0.15. And finally, we give it a large value for the last one, about 500, and the value of 0.75. So remember, if you have a possibility of the problem having the damping characteristics, you need to assign a damping. In this case, we're going to give it the mass proportional damping value of about 25. I need to remind you that you always need the density for explicit dynamic solution. That's a requirement. We create a section, a solid section, generic one, and with the material that we call aluminum, and we assign the section to that. I'm going to uncheck the create set and say OK. Now we create a second part. This one is going to be a rigid plate, and that's going to be acting as a ground where the solid is going to hit. So we're going to do analytical rigid, extruded shell. Just draw a horizontal line, give it the dimension of 100, which is what we're going to do here. And then we're going to extrude that by 200. We'll give it a reasonably large plate, so when the impact occurs, upon bouncing up and then the part wanting to fall over again, we don't want it to fall off the edge. We want it to fall onto the plate again, so it'll simulate the effect of bouncing on the ground multiple times. All right, with this in mind, we need to make sure we have a reference point on the analytical plate to be able to restrain that. To create the reference point, the first thing we want to do is create a datum point. We're going to create the datum point midway between the 2 points. Pick the end 2 points that you see at the center. The datum point has been created here, and now we're going to go ahead and say Tool, a reference point and pick the datum point, and automatically the reference point will be created. Now we're done with that. We're going to create the assembly, and go ahead, open the assembly instances. The first thing I would do is auto offset from instances, pick the two parts and say OK. And notice the orientation. I want to rotate this thing slightly so the point of impact would be close to this bottom edge or corner that I've highlighted. So first things first, we're going to rotate the instance, which is going to be this instance. We're going to say the first point for the axis of rotation. We want the z-axis, so the first point is 0, 0, 0. You'll put the cursor inside and press enter. The next point is 0, 0, 1. That corresponds to a positive z-axis. Angle of rotation, we'll give it the 30 degrees and see what happens. I will say enter. That's opposite of what we want. So instead of saying OK, we'll do the back to the previous step, and we put the negative sign in front of the 30 degrees and say enter. We're good to go now. And be sure to say OK at this point. And now we're going to translate that to coincide with the reference point. Translate this instance, pick that bottom corner point, and say I'm going to pan out to the RP. And if you look carefully, you notice there's a possibility of some interference. Unless you're 100% sure, I would highly recommend that you translate that upward a little bit. So we're going to translate this instance again. Starting point for the vector. The vector is going to be along y direction. The first point is 0, 0, 0. Next one is 0, 1, 0. Is the position okay? That's a little bit too much, so I'm going to go ahead and back out. So we're going to say 0, maybe 0.10, just ever so slightly above the plate, just like that. If you zoom in carefully, you can see what we're talking about here. Very, very much so above the plate. Now, if you're not 100% sure, go ahead, give it a more reasonable dimension, such as in this case, I'm going to give it 1/4 millimeters, so 0.25, and say enter, just to be completely sure that you are right above the plate and there's no possibility of any kind of interference, as you see from this drawing. Okay, so now that the part is oriented, you say OK, and go ahead, create a step. The step is going to be explicit impact, we're going to call this thing, and the procedure type is going to be a dynamic explicit. Continue. Time period, we're not going to give it a very long period of time. We're going to say 0.1, and be sure under the other tab, the bulk viscosity, both linear and quadratic are turned on, especially the quadratic one that is important for high-speed events such as impact phenomenon. A field output request will switch the interval to 100 to get enough data points for visualization, and the history should be 200 data points, which is good. Now we're going to go ahead and try to create contact interactions. So we're going to start interaction property. That's going to be contact interaction, and we'll say continue. We'll start with the tangential behavior. We'll give it a coefficient of friction under penalty regime of about 0.15. And then under the normal behavior, we accept the default, including allowing separation after contact. Now, if you were to start interaction right now and say you want to create the general contact interaction, when you say continue, it'll complain that the rigid plate is analytical one and has not been referenced by any sort of the surface. So as a result, what I would like to do is go ahead under the assembly instances, under the surfaces, double click on the surface and call that the rigid surface. Continue and pick the rigid surface and say done. It'll give you the choice of two colors, brown and purple. If you go underneath, that's the purple, on top is brown. Clearly we want the brown to be the surface of contact. Now we're going to go ahead and create the interactions. Under interactions, general contact, we're going to say contact explicit is what we want to create. We'll say continue, and we will pick the default all with self. That allows you the possibility of other surfaces of the main part to be contacting regions of the rigid body, as well as self-contact possibility. Unless you're 100% sure which surfaces are making contact or will be making contact, I would suggest you leave it at that. Otherwise, you can pick the selected pairs and identify which pairs will be making contact. Don't forget to pick the global property assignment. So now we're going to go ahead and assign the boundary conditions. The first boundary condition will be assigned to the rigid one. That's going to be the rigid fixed boundary condition. We'll pick the reference point and fix the whole thing, and that allows the rigid plate to act as immovable ground, perfectly fixed. Okay, now we're ready to define the impact velocity. You assign that to the main part. You do that under predefined fields. And instead of the step being explicit impact, you want the initial step, because that's the initial velocity. So we say velocity input as the step name, and instead of temperature, we'll go to the mechanical and pick the velocity and say continue. Carefully drag and select the entire volume, not the surfaces, and just say done. We're going to go ahead and assign velocity in the to direction of negative 120 millimeters per second, and that should take care of it. Now we'll go ahead and assign the mesh, and the mesh obviously assigned to just the main part, and from the color it should be clear to you that the program thinks it can do sweep meshing. We'll go ahead and assign element type, and that's going to be explicit element. Don't forget that one. Hexahedron reduced integration is default. Let's just accept that for the time being. And then element shape is hex. Sweep meshing, as you're suspecting. And then go ahead and give it the seed part. Let's make that 1.2 as the seeding, 1.25 maybe. We'll say OK and mesh the part like this. You have about 1800 elements from the prompt region. And now we're going to go ahead and create a job. This is going to be impact explicit solution. Don't forget to save your work all the time. And I'm going to go ahead and submit this thing. Let's go ahead and monitor the results or the execution, and click on the warning tab. You'll see the default information. This is not necessarily a warning that is going to cause problem in the execution. It's simply telling you that the specified boundary type is the displacement in the explicit analysis, so that you can check for possibility of jump. You'll notice if I go way up, if I can try to stay there, the kinetic energy initially very high and then drops down dramatically because it is making impact, and then you'll see it bounces around a few times. The kinetic energy is changing, the total energy is remaining the same. Stable time increment is pretty much in the order of 3 times 10 to the minus 6, and the execution is finished. We're going to dismiss, right click, look at the results. And the only thing I want to look at this point is under Create XY Data, ODB History Output. Let's look at artificial strain energy versus the internal energy and plot that. And please note the variation of the two. You will note that your artificial strain energy is becoming a significant, almost 10% or higher, of your overall internal energy. That should give you a warning that indeed your model has some hourglassing situation or spurious shear or stiffness associated with the shear, meaning that the reduced integration formulation is not behaving properly. So my suggestion is that at this point, dismiss that. Don't even bother looking at the stress or strain data. And this is a clue for you to go back and change to the mesh again. And look what we're going to do. We're going to assign element type, uncheck the reduced integration, and just for good measure, we're going to go ahead and refine the mesh a little bit, make it 1.0 for the approximate global size. Automatically delete the meshes and then mesh the part. Now we, instead of 1800, we have 3420 elements, and we're going to go ahead and run the model with the new mesh. And if you look at the monitor, you will see things will move a little bit more slowly. You have a lot more elements now. And let's look right off the bat, look at the kinetic energy and see how it is high and then it goes down as it makes impact, and it then starts bouncing around a little bit. And we will look at this thing again when the execution is finished, and we'll look at the results. If you run this model yourself, you notice that it's going to take a while for it to run, and also please note, because of the number of elements and nodes, you can't run that with the student edition of the software. You have to go to education edition or the research edition. So we're going to dismiss this and look at the results. Once again, we're going to first look at the ODB history output. Same thing as before, artificial strain energy and internal energy of the system. Select both using control and then plot them. Regrettably, the colors that have been chosen are not very good. Now you can see it a little bit better. The red is the internal energy, or the orange, depending on how you're looking at it on the screen. And then the blue down below is the artificial strain energy, which is now perfectly flat at 0, means that you have a very good mesh that can approximate this behavior well. And you'll notice the internal energy is damping out. Part of it is because of the viscous dissipation. I can look at the viscous dissipation versus the kinetic energy, for instance, and plot both of those guys, and you'll see how that looks like. Kinetic energy very high, as you would expect, and damps out. Viscous, on the other hand, keeps going up, and then kind of tapers off a little bit, but still keeps going up because structural inherent structural damping is going to be there, and it's just going to take effect and absorb more of the energy of the system. And finally, if you want to look at the strain energy and compare that with the artificial strain energy, you can plot those, not in these colors, we'll plot them. And again, strain energy kind of follows the pattern of the internal energy of the system, and you'll notice the flatlining and very close to 0 of the artificial strain energy. Now we're going to go ahead and look at the results. The way we're going to do that, look at the frame selector, go back to the frame 0, look at the stress values, and if I'm going to rotate that a little bit to show you how the impact is taking place, it is hitting the plate, going back up, and it just keeps going up. Now you're wondering why that is the case. Remember, this program just does the mathematical approximation. It has no clue about effect of gravity or the weight. Of course, you're going to say, well, the more realistic representation would be if I were to apply the gravity or the weight to this thing. You would be correct. So we're going to go ahead and now modify the problem. Simply double click on the load. Instead of initial, we're going to do explicit step and say gravity load, and be careful with the unit. Again, we're with the millimeters, so we're gonna say 9.81 meters per second squared. It's gonna be in terms of the millimeters per second squared, so it's gonna be minus 9810. And we'll say okay. So now you've added gravity. In case you want to observe that, your part coordinate system or the assembly reference coordinate system will show the vector that is corresponding to gravity, and you can run the model again with the gravity and see what happened. You'll notice the number of increments that it's taken for it to solve the problem. Once again, now that we have solved this including the gravity, we're going to look at the results. Sometimes you may get this message. That's okay. Let's do it again and look at the history output one more time. Artificial strain energy, internal energy. You still see that now with the inclusion of gravity, the damping and the of this internal energy is more substantial, and also your artificial strain energy is close to zero. Now you can see more pronounced representation of where the bouncing is taking place at these peak values, and that is done with the kinetic energy comparison with that of maybe strain energy. If you plot these two together, you will see that the kinetic energy and strain energy pretty much are opposite of one another. As kinetic energy is high, there's no deformation. Deformation starts when the kinetic energy starts dropping down, that you can see in blue. As kinetic energy reaches the minimum, the strain energy reaches the maximum value. It's just a classic case of conversion of velocity into the deformations internally. And that phenomenon keeps repeating itself, except for some instances that you'll see why. And we're going to dismiss that, go back to the some output plot. We're going to plot the deformed shape. This is the deformed shape at the last step. We can look at the frame selector and go to frame selector, bring it down to 0, and zoom in a little bit. So we'll see that we're looking at the stress results. As you start, it hits the ground, bounces, and it just eventually settles down. And because of the effect of gravity, it starts falling over. We didn't give it enough time to see the effect of it falling over because it will take much more computation effort to see that. We just wanted to see a sample of the output. And in addition to that, just check the plastic deformation. You'll see the plastic deformation where it is taking place, as you're expecting. That's how it is going to be. And so far as plotting is concerned, we can do an undeformed shape plot and then go create XY data, ODB field output. Let's get rid of this thing and say continue. And we're going to pick unique nodal, and we're going to look at the 1 mesostress, and maybe as well as plastic strain equivalent. Pick the element nodes, and I'm going to pick let's say this node here. Plot that. We didn't pick the entity. We have to do edit selection, so it'll pick that point and say plot. You will see that the if I were zoom back out a little bit of this plot, the stress is the one that is in red. I'm going to replot that so colors will be a little bit more distinct. Yes, that's much better. The stresses are now plotted in blue, and the plastic strain is plotted in red. You notice that because of some secondary change in the value of the stress, the strain also has gone up accordingly. Although this may be looking ominous, but you notice the change is not really all that much so far as the plastic strain is concerned. So far as the stress is concerned, we go from about 100 MPa to about 120 some change MPa, and that's the secondary bouncing that takes place at a time of about well, let's find out what time it takes place. We'll go ahead and probe the values and move around until we hit this value, which is about 0.064 seconds, at which time this phenomenon is taking place. So these are the kinds of output that you can request and take a look at for the explicit dynamic solution. And this concludes our looking at the explicit solution. The only other thing I may want to do is look at the contact pressure for the output. And the contact pressure in this instant is non-existent. So let's go from the beginning and gently move the slider. You'll notice the contact pressure changes. That's indicative of at what instances the body is making contact with the rigid plate. That's why you see the flashing effect, meaning only at certain time intervals the contact is effective and other times it is not. This is perhaps the most pronounced form of the contact that you will see. So that's another output that you can take a look at. All right, we will end that at this point.